Characteristics for the occurrence of a high-current Z-pinch aurora as recorded in Antiquity by Anthony L. Peratt, Fellow, IEEE. IEEE Transactions on Plasma Science, Volume 31, Number 6, December 2003. Narrated by Electric Universe. The discovery that objects from the Neolithic or early Bronze Age carry patterns associated with high-current Z-pinches provides a possible insight into the origin and meaning of these ancient symbols produced by man. This paper directly compares the graphical and radiation data from high-current Z-pinches to these patterns. The paper focuses primarily, but not exclusively, on petroglyphs. It is found that a great many archaic petroglyphs can be classified according to plasma stability and instability data. As the same morphological types are found worldwide, the comparison suggests the occurrence of an intense aurora as might be produced if the solar wind had increased between 1 and 2 orders of magnitude millennia ago. 1. Introduction. On July 9, 1962, the United States detonated a 1.4 megaton thermonuclear device in the atmosphere 400 kilometers above Johnston Island. The event produced a plasma whose initial spherical shape striated within a few minutes as the plasma electrons and ions streamed along the Earth's magnetic field to produce an artificial aurora. The figure you see here is a photograph of the artificial aurora 3 minutes after detonation as recorded from a KC-135 aircraft. Concomitant with the artificial aurora was a degradation of radio communications over wide areas of the Pacific, lightning discharges, destruction of electronics and monitoring satellites, and an electromagnetic pulse that affected some power circuitry as far away as Hawaii. The event was recorded worldwide as the plasma formed at least 2 intense equatorial tubes, artificial Van Allen belts, around the Earth. These tubes, or plasma toroids, contained relativistic electrons bound by magnetic fields, the source of intense amounts of synchrotron radiation. The radiation lasted far longer than expected. The decay constant was of the order of 100 days. Mankind, unknowing, has viewed synchrotron radiation from the Crab Nebula for centuries. The only known mechanism that produces synchrotron radiation are electrons spiraling about a magnetic field at nearly the speed of light. Thus, the shape of the phenomena as recorded at radio, visible, and high frequencies was that of plasma donuts encircling the Earth, which mimicked the Van Allen belts. The artificial aurora shown here also shows plasma striations that arise from instabilities. This paper describes characteristic features of laboratory plasma experiments and simulations, especially for high-current Z-pinch conditions, and compares these features with petroglyphs and other ancient writings, which may have been associated with auroral observations. As in the natural aurora at the northern and southern magnetic poles, the streaming charged particle electrical currents, Birkeland currents, are of the order of megaamperes. 2. Dynamics of an intense aurora. The shape of the aurora is determined by the supersonic solar wind, Earth's magnetospheric shield approximately 100 kilometers above the Earth's surface, and Earth's dipolar magnetic field. It is the magnetopause that diverts the impingement of the solar flux into a teardrop-shaped shell. At the widest, the width of the magnetopause is of the order of 130,000 to 150,000 kilometers, while the tail may stretch away from the Earth far beyond 1 million kilometers. For comparison, the mean distance between the Earth and Moon is 384,402 kilometers. The circular or oval inflowing and outflowing electrical currents are shown here. These sheets of electrical currents form the rapid waving curtains of light in an auroral display, a result of the electrons interacting with and exciting molecules in the upper atmosphere. The aurora is sporadic, usually lasting for a maximum of several hours, but sometimes for days. The most intense and largest auroral displays occur during a solar storm when the incoming flux increases dramatically. 3. Instability of the auroral sheets. A. Auroral morphologies. The auroral plasma column is susceptible to 2 plasma instabilities, hollowing of the relativistic electron beam to form the sheets and the dielectron instability that caused the sheets to filament into individual current strands, causing the swirls or curtains. These instabilities also produced the radiation observed over a wide range of the electromagnetic spectrum. The dimensions of the auroral circle can be hundreds of kilometers in diameter, while the width of the sheet can be tens of thousands of kilometers. For an intense inflow of plasma, the aurora would be shaped by the strength of its own azimuthal magnetic field, i.e. a Z-pinch. In the case of a strong aurora involving many tens of megaamperes of current, most of the funnel would be visible in light emission and the individual filaments and vortices strongly visible. In a narrow field of view, the light-emitting filaments would appear as dots or elongated dots and filamentary strands. This geometry would predominate if the charged particle outflow from the sun were to increase an order of magnitude or more from an appreciable length of time. In addition, portions of the magnetosphere and its tail would also be visible. This figure is a graphic depiction of an intense auroral funnel. The thin outer plasma has filamented into small diameter plasma currents and inner plasma sheets and core. The upper part of the funnel has either a diamond, mottled, or cellular structure, while the incoming part of the funnel consists, looking up, of concentrics of dots and cylinders. The instabilities that occur in the mid to bottom part of the funnel will be a topic of study in this paper. For an intense aurora, the converging filaments are seen not only as dots, but also as dots connected to the visible converging filaments at higher altitude. We shall delineate the aurora plasma sheet into two parts, the upper funnel or inflow region and lower plasma sheet and solid columns. B. Auroral luminance. Charged particle excitation from the inflowing plasma is responsible for the luminosity and color of atmospheric auroras. The color depends on the upper atmosphere's state and height above the Earth. Various de-excitation processes in atoms of oxygen and nitrogen cause mostly green, red, and blue auroras. Exceptionally yellow auroras can be observed in places where red and green auroras overlap. Observations suggest that the geomagnetic storm producing an energetic aurora derives from the direct injection of electrons from the solar plasma flux. In fact, the source of the high-energy electrons need not necessarily be solar, but may be an electric space phenomenon that causes an inflow of plasma to the Earth. An update of research in solar plasma, interaction of solar and the Earth space plasmas, geomagnetic storms, substorms, and aurora, the magnetosphere and ionosphere, and the simulation of space weather may be found here. 4. Experimental and analytical methodology. The experimental data was taken from various terawatt power machines, with the majority of the data taken by the author on the Maxwell Laboratories Blackjack 5 pulsed power generator. Data was also drawn from the U.S. Department of Energy Laboratories pulsed power facilities at the Los Alamos National Laboratory and Sandia National Laboratories. High explosive generators in the U.S. and Russia added to the data set. The currents ranged from hundreds of kiloamperes to 150 megaamps, and timescales from tens of nanoseconds to microseconds. The plasma load geometries were generated by applying high voltage pulses to gas puffs to simulate an aurora-like plasma inflow, wire arrays to simulate filamentation dynamics, and concentric plasma sheets formed by nested cylindrical foils to produce high-velocity shock waves. In size, the geometries were a few centimeters in diameter and 2 to 3 centimeters in length. A. Diagnostics. The diagnostics generally included laser shadowgraphy, Schlieren photography, laser double pulse holography, fast framing cameras, streak cameras, X-ray detectors, bolometers, soft and hard X-ray pinhole cameras, Rogowski coils, and waveform recording probes. In some experiments, thermoluminescent detectors measured the photon spectrum, electron energy spectra, Bremsstrahlung spectrum, and their angular distribution. B. Solution of Chandrasekhar-Fermi equations on high-performance computers. Theoretical and computational analysis of a plasma column are based on a fundamental plasma theorem for conditions of dynamical stability. This theorem was first used in magnetohydrodynamics, or MHD, by Chandrasekhar and Fermi to establish the condition for dynamic stability of cosmic gravitational masses balanced by gravitational, magnetic, and kinetic pressures. The basic geometry under consideration by Chandrasekhar and Fermi was cylindrical, as was that of Shafranov, who extended the use of the theorem to investigate equilibrium conditions for current-carrying plasma columns. Extension of the theory to account for three-dimensional or 3D kinetic motions were carried out by Peratt, Green, and Nielsen, who benchmarked the computations against both low and high current plasma columns with 3D relativistic particle codes. Verification and validation of the computer codes are a necessity. All simulations are benchmarked to high energy density data. Similarly, experimental data are benchmarked to the simulations to understand the column evolution. 5. Evolution of the high current Z-pinch. The overall time history of the pinched column from formation to eventual breakup has been a topic of some interest. The evolution is studied with the 3D electromagnetic and relativistic particle in cell simulation code Tristan. Other works on the topic are found in the literature. Overall, the data give a picture similar to that shown here, where inflowing plasma converges into a striated or patterned plasma column. A. Instability of a solid plasma column. A solid plasma column, such as that shown in the center of this image, is susceptible to two types of instabilities. The m=1 or helix is a common instability in both laboratory and space plasmas and occurs when a magnetic field axial to the column pre-exists. It is not unusual for a plasma to produce a circular magnetic field with a slight vertical component that rapidly develops into the axial field needed for the development of a helix. This figure shows examples of both cases, respectively. Increasing the current in all cases produces a smaller diameter helix. B. Column structure. The morphology of the Z-pinch as it evolves in time is that of a self-organizing structure of an outer spheroidal plasma envelope and inner toroids as discussed by Ortiz, Tapia, and Cubes. Generally, in an intense electrical discharge in the multi-megavolt, multi-megaampere range, as would be measured in an intense aurora, 9 distinct pinches that are spheroidal in shape are formed. While there is no known theoretical basis for 9 spheroids, experimentalists most often mention between 8 and 10. In this figure, the bottom 2 were cut off in the recording. These spheroids, or plasmoids, consist of an outer spheroidal plasma envelope and inner toroids that define both the magnetic fields and the currents within them. 1. Spheroids. The frames in this figure portray the outer spheroid isophotes, some including the central visible core. The central plasma core is not plotted in the simulation. The pictures on the left are the X-radiographs, while that on the right is a computer simulation. Generally 1, 2, or 3 plasmoids are visible at a time, but as many as 8 are common. It is also not unusual to find a truncation or modification of the topmost spheroid. 2. Inner toroids. Intense optical radiation, synchrotron radiation, and X-rays are recorded from the inner plasma toroids. The basic geometry is shown here, where A is the basic geometry, B is a framing camera picture of the centimeter size 1.3 megaamperes pinch, C is the centimeter size 6 megaamperes pinch, and D is the centimeter size 6 megaamp pinch, which optically dense or brightest plasma is shown. Note that the densest plasma forms the top feature, the sides with the toroids, and the bottom base that flares downwards and away from the column. 6. Evolution of the plasma column toroids. In pairs, the electromagnetic forces on the toroids in the stacks shown here are long-range attractive, short-range repulsive, or force-free, or merging. However, in a stack, the repulsive attractive forces tend to flatten all but the top and bottom toroids. This is illustrated on the left. A pinched plasma X-ray radiograph is shown on the right side. The top radiograph is a plasma column with sinusoidal pinch perturbation at early time. On the bottom, the radiograph shows that these ripples have rapidly converged inward by the intense self-magnetic pressure to produce flattened toroids. The radiographs in this figure are sequential, measured in the X-ray regime after column formation. The total current conducted through a 4 centimeter column diameter was 16 megaamps. The bottom toroids appear to be cut off photographically, but this is the actual untouched radiograph. The experimental data set is a complete time motion sequence of the Z-pinch. Selected radiography frames and simulation graphs have been assembled in this figure, the later of which is a time sequence of a multi-megaampere stack of toroids in the highly nonlinear instability phase. Time proceeds from left to right and top to bottom. The current conducting plasma column shown starts from a previous nonlinear phase where the pinch ripples on the outer surface have collapsed into squared, folded, and warped toroids. As shown in time 1, the maximum number of toroids are those of the initial outer spheroid envelope, 9. However, as the current increases, the toroids come under intense self and neighboring toroid pressures, forcing dramatic toroid deformations. In the data depicted, the topmost toroid folds into a bulb-like shape. Time 2 illustrates the flattening of all the toroids, such as those shown in this figure, bottom right. With increasing current, the toroids warp violently and produce well-defined vortex curls at their edges. These edge vortices wrap up in a spiral. In some cases, the folding may be flat or square, as is the flattened toroid. The edges curl in and out and upwards and downwards to the current flow. In some cases, mushroom-like structures form as shown in the center frames, time 3. For increased current at later times, the center toroids are forced to merge, reducing their number as shown at time 4. The central toroid can be tubular, flat, or spheroidal. Time 4 also illustrates the effect of luminosity on the morphology observed. 7. Hydrodynamic shockwave patterns from auroral shocks and colliding plasma sheets in the upper atmosphere. The auroral electrical circuit is by far the best known of all space plasma circuits. It is derived from a large number of measurements in the magnetosphere and ionosphere. Above the lower atmosphere, at about 100 kilometers, multiple layers of plasma form the ionosphere. The auroras occur in the lower portion of the ionosphere, primarily from about 90 to about 150 kilometers, as the result of electrons interacting with and exciting molecules in the upper atmosphere. Prehistoric man at northern latitudes often likened the patterns produced to the butting of goat's horns in combat. The inflowing currents are relativistic particles with velocities approaching the speed of light, and sporadic, producing high Mach number shocks at interfaces in the intense current plasma column. In addition to the vertical particle flows are shock surface phenomena produced by the impingement of the outer shell on the inner shell, forming an extremely intense aurora, when the outer shell stagnates at the main plasma column. At early time, a number of unperturbed surfaces exist that are susceptible to shock-induced instabilities, outlined by Zeldovich and Razier. For example, the outer cylinder surfaces shown in this figure eventually slam into the inner cylinder surface whose inward acceleration has been stopped by the plasma it compressed. Other planar surfaces susceptible to shock instabilities are the upper atmospheric strata. It is these layers in which we observe the auroral curtains and instabilities today from sporadic high-intensity electrical pulses traveling along the auroral column. At a planar interface of gas or plasma, a shock pulse initiates a series of hydrodynamic instabilities that differ from the plasma column instabilities. In hydrodynamics, these are Freischmeyer-Meshkov instabilities recorded by Buzzini and Benjamin. Initially, a pulsed perturbation on a denser layer causes a rippling of the layer that rapidly develops into periodically spaced spike-like features. These features, or spikes, then evolve in a way shown in the top frame of this image. The first frame of a laboratory simulation of the time evolution of an ionospheric layer shocked by a Mach 1.2 pulse. Time increases from left to right and top to bottom. As shown in the sequence, the shock impulses causes the generation of yet more instability spikes that themselves morph into yet more complex instability shapes. The centermost feature, the point of shock impact, has changed appreciably from its initial spike profile into a tripling of morphology associated with fast instability growth. 8. Electrical discharges associated with intense auroral currents. A. Lightning. Strong electrical discharges are associated with intense inflowing charged particles. This is the lightning most often seen in connection with atmospheric discharges whose tortuosity are the jagged and complex light strokes seen in the sky and accompanied by the sound of the shock wave. B. Heteromax. Kukushkin and Rantsev-Kartanov at the Kurchatov Institute, Moscow, Russia, found that, based on fractal dimension analysis of experimental data from plasma pinches, electric current-carrying plasmas are a random fractal medium. The basic building block of this medium was identified by Kukushkin and Rantsev-Kartanov to be an almost closed helical filamentary plasma configuration called a heteromax. Heteromax are coupled together through long-range, self-sustained filamentation and thus forms a dynamical, percolating network with dissipation. Hence, heteromax can include filamentary, cellular, and bubble-like clusters. Heteromax tend to repeat a pattern at increasingly smaller sizes in a random matter. The tendency of heteromax is to display the plasma in random fractal, self-repeating and overlaying patterns. 9. Petroglyphs. Petroglyphs, the carving of pictures on rock, have mystified and inspired historians, archaeologists, anthropologists, shamans, religious cults, and even some astronomers for centuries, if not millennia. They are found on every continent except Antarctica. Some are mere scratches, while others are chiseled centimeters deep. Petroglyphs, or rock art, are thought to date back to the Pleistocene and Paleolithic, the earliest markings by man on rock. While the dating of petroglyphs has been a high priority for all who study or record them, there exists no consensus that an absolute age can be attached to any one pre-Columbian petroglyph. Differing exposures to the elements lead to differing durability, coloration of the rock's patina or desert varnish, a natural coating of manganese, iron oxides, and clay minerals, and lichen overgrowth. The uncovering of the Glorieta Mesa and Roe Mesa horizontal petroglyph sites from under 1 meter of earth near Santa Fe, New Mexico, might give the best indication of the ages of some petroglyphs. Campfire remnants some centimeters above the petroglyphs suggest that they are at least 4,000 years old. In this paper, we shall limit the study to petroglyphs thought to range in age from 10,000 to 2000 BC. A. Von Humboldt pioneered the recognition of the social importance of information carried in petroglyphs. From 1799 to 1800, while exploring the hydrographic anomaly of the Cassiquiare, a natural canal joining the Orinoco River of Venezuela with the Rio Negro of the Amazon basin, von Humboldt observed petroglyphs high on a bluff, which prompted his advocacy that pre-Columbian civilization, far from being primitive, was the remnant of once higher societies in South America. Concurrent with Humboldt's exploration of South and Central America, Russia, and China, the Lewis and Clark expedition detailed their horticultural, geological, anthropological, and geographical findings of the American Northwest. On April 23, 1806, Lewis and Clark made their campsite on the Columbian River between 4 O'Clock Rapids to the east and John Day Bar to the west, near what was named Hieroglyphic Rocks. According to Wilkes, about 8 miles above their encampment, they came to the Hieroglyphic Rocks. These are about 20 feet high, and on them are supposed to be recorded the deeds of some former tribe. Nearly 100 years later, Colonel G. Mallory, in an 1882 to 1883 report entitled Pictographs of the North American Indians, a preliminary paper, voiced a much different opinion of petroglyphs. In fact, the title of his later work is far too modest. Picture Writing of the North American Indians is probably the most comprehensive study of petroglyphs worldwide. While the extent of Mallory's work is unparalleled, the interpretation of the phenomena is totally consistent with the regard in the late 1800s of the American West's perception of the Indian and other primitive peoples. For example, in the introduction to his work, Mallory paraphrases Sir F. Bacon in saying that pictures are dumb history. Mallory assigned various meanings to the petroglyphs that would be concordant with the beliefs of Western settlers or Native Americans at that time. However, Mallory's interpretation of petroglyphs is thought of the mind as a concept that remains with us today. His uneasiness with attributing this concept to petroglyphs is probably best illustrated by his statement, "The remarkable height of some petroglyphs has misled authors of good repute as well as savages." Petroglyphs frequently appear on the face of rocks at heights and under conditions which seem to render their production impossible without the appliances of advanced civilization, a large outlay, and the exercise of unusual skill. Hence, like Humboldt, Mallory perhaps unconsciously subscribes to the idea that petroglyphs are other than primitive ritualistic scratchings. 10. Petroglyph data. The data shown in this paper were taken from a data bank containing several tens of thousands of digital petroglyph photographs, many with their GPS longitude and latitude positions and orientation with respect to the most probable field of view. In the American Southwest and Northwest, data was acquired by two teams of physicists, geophysicists, Bureau of Land Management employees, students, and petroglyph site stewards. Permission was obtained from both the U.S. Department of Energy and the U.S. Department of Defense to photograph petroglyph sites not accessible since 1943. In situ investigations allowing direct digital recordings of the petroglyphs, notations of terrain and fields of view as well as global position satellite measurements were carried out in New Mexico, Texas, California, Utah, Arizona, Nevada, Colorado, Oregon, Idaho, Washington, and British Columbia, Canada. Data from other known petroglyph-rich sites in the Midwest and northeastern U.S. was also included, as was data from Loring and Loring, Thiel, Schaafsma, and Juncken. The methodology included determining the most probable field of view, the position occupied, terrain or local obstacles, and degree of shelter most probably available to the artist. Special attention was given in this regard to work-intensive, deeply carved, or precisely drawn petroglyphs. Some, after carving, were then polished and painted. Other items of note were landslides, primarily of massive boulders partially covering petroglyph panels, panels whose faces had been partially cleaved by the elements, and boulders whose petroglyphs had been split by the cracking and separation of the rock itself. Access to sites of habitation and overall accessibility or inaccessibility to the petroglyphs completed the survey. Worldwide, most of the digital petroglyph data was acquired from the following places or countries and from regions adjoining them: Africa, Argentina, Arizona, Armenia, Azerbaijan, Bolivia, Borneo, Brazil, California, Canada, Canary Islands, Central America, Central Asia, Chile, China, Colorado, Colombia, Dominican Republic, Easter Island, Ecuador, Egypt, England, Ethiopia, France, Germany, Gibraltar, Greece, Guyana, Hawaii, Idaho, India, Indonesia, Iraq, Ireland, Israel, Italy, Kashmir, Korea, Malta, Mexico, Macedonia, Malta, Minnesota, Mississippi Valley, Morocco, Nambia, Nevada, New Caledonia, New Guinea, New Mexico, Nicaragua, Norway, Okinawa, Oklahoma, Oregon, Pakistan, Panama, Paraguay, Pennsylvania, Peru, Portugal, Russia, Scotland, Siberia, South Africa, Spain, Sri Lanka, Sweden, Switzerland, Tahiti, Tibet, United Arab Emirates, Uruguay, Utah, Uzbekistan, Venezuela, Washington State, and Yemen. Most of this data was contributed by individuals residing in or having collections of material from these regions. Finally, the data was cataloged according to morphology and plotted on 3D computer renditions of scanned topographical maps. The results of this survey entailed a most probable field of view of the artist for differing petroglyph types and mapped the skewness inherent in the drawing. The data shows that petroglyphs have a preferred orientation on a worldwide basis and on morphology type, indicating that they are reproductions of plasma phenomena in space. These results will be presented in another report. 11. Data carried in petroglyphs. Petroglyphs are images created on rock by means of carving or pecking the outer surface to expose the surface underneath. Most rock surfaces, independent of the chemical composition, are covered by a thin layer called a patina or varnish. This patina is created naturally by the rock's exposure to the elements. Rain, snow, sunlight, and extragalactic radiation such as gamma rays interact on the surface with salts and minerals, and even the crystalline structure of the rock, creating a thin outer darkening of the rock, a natural coating of clay minerals, manganese, and iron oxides. Prehistoric man would chisel or peck away the patina and expose the original stone surface to create the petroglyph image. Rock panels that derive from volcanic basalt are favored for petroglyph recordings. However, carvings and other materials were also used. A frequent way of recording was the use of scratch petroglyphs, where scratches with a sharp stone were used to create patterns. Pictographs that in this report are placed in the same category as petroglyphs are made using paint instead of carving into the rock. Other objects from antiquity, statuettes, pottery, and structures are also placed in this category. Delineation will be presented in a following paper. While single petroglyphs may be found, petroglyphs are most often found grouped in selected sites by the hundreds or thousands. Sometimes the same rock facing has been overwritten 2 or 3 times. The appearance of such sites is one of random disarray of crudely drawn animals, people, unrecognizable anthropomorphs, and abstract patterns or symbology. A rich cache of petroglyphs consisting of many hundreds or thousands of figures. Petroglyphs may be found in readily accessible places or in highly precipitous locations, in the open or within crevices. Generally, the discovery of one petroglyph results in the rapid spotting of dozens or hundreds more. The paper will suggest a rationale for petroglyphs being carved in difficult or specialized locations when equally satisfactory rocks in more readily accessible locations are in the vicinity. For example, the line of sight to the Earth's magnetic poles and highly conducting regions on the Earth's surface. These are the criteria of an intense aurora today. Its appearance at the magnetic poles and the subsequent electrical damage to conduction paths such as the Alaskan oil pipeline. A common image among petroglyphs is lightning-like discharge figures. 12. Association of petroglyphs with an intense aurora. The study of the aurora has been one of gathering as much information as possible about the influx of particles from space and its effect on Earth's space, plasma environment, and upper atmosphere. As such, the aurora is a stimulus to improved laboratory work on many different processes important to plasma physics. However, the purpose of this paper is neither of these, but rather an attempt to explain how in man's prehistory recordings of high energy density phenomena, some not experimentally recorded until the last few years, could have been carved on rock in an accurate, systematic, and apparently temporally reliable fashion. 84 distinct high energy density Z-pinch categories have been identified in petroglyphs, nearly all of which belong to the archaic class. Only a small percentage of these petroglyphs or parts of petroglyph patterns do not fall into any of these categories. This figure shows 10 examples of a single category of petroglyph found worldwide. The anthropomorphic man, with or without the side dots, called a squatter by rock art collectors, is recorded everywhere. On the large rock panels such as this figure, overlaid petroglyphs are often heteromax, figures with yet smaller figures attached inside or nearby. As the displayed figures in the sky evolved, perhaps over a decade, other overlays were added to represent the changes. Thus, association of petroglyph morphologies allows an epoch of electrical discharge evolution to be extracted from the carvings. A very small sampling of petroglyphs drawn in the heteromax format is shown in this figure. A. Direct comparison of plasma phenomena with various petroglyph morphologies. This figure is a comparison of petroglyph images to both experimental and computational recordings of a plasma pinch. The frames on the left are radiographs of the pinch. The middle frame is a high-fidelity computer simulation of a plasma pinch, while the images on the right are a selection of petroglyphs typical of this morphology. In the visible, the central plasmoid stack, or parts of it, would be observable dependent upon both the location of the observer and the duration and location of a current pulse propagating along the column. Because of the time required to produce certain classes of morphologies of petroglyphs and also the precipitousness of location, we conclude that petroglyphs were produced during daylight conditions, perhaps twilight or dawn. This then allows an estimate of the luminance necessary to see auroral plasma phenomena. 1. Spheroids. The petroglyphs in this figure accurately portray the outer spheroid isophotes, some including the central visible core. The central plasma core is not mapped in the simulation. Generally 1, 2, or 3 plasmoids were visible at a time, but as many as 8 are common. It is also not unusual to find a truncation or modification of the topmost spheroid. 2. Inner toroids and surrounding features. A more impressive sight than the outer spheroid shell would have been the intense optical radiation from the inner plasma toroids shown in this figure. The petroglyphs to the right are typical of those commonly found in a stack of circles. One of the petroglyphs has captured the optical radiation from all 9 toroids. The middle isophotes reveal more detail. A totally unexpected feature appeared when the isophotes were artificially colored, such as, quote, nose and eyebrow features. These features are shown in this figure, the so-called petroglyph eye masks and the face masks. 3. The separatrix X points. An appreciable number of petroglyphs have captured the separatrix pattern between plasmoids with rather high fidelity. The script-like X separatrix should not be confused with the well-defined circle-enclosed square-cross petroglyph. The complete patterns containing the X-type separatrix are shown in this figure as numerically generated from the Chandrasekhar-Fermi equations for a plasma column. The diversity of cultures preserving common rock art themes is apparent in the separatrix patterns. 13. Evolution of a columnar stack of plasma toroids. In rock art terminology, the experimental image shown on the right side of this figure would be classified as a caterpillar and a ladder. These are reproduced again in this figure. The sequences shown correspond to the rise time portion of a long current pulse, increasing electrical current. A. Caterpillars and ladders. This figure shows the experimentally reproduced conceptual geometry. The inner toroids have been flattened while the uppermost toroid has folded inward, like the closing of a petal of a flower, into an oblong-shaped object. The second uppermost toroid is also starting to fold upward. The increasing current has also started the warping of the flattened toroids as well as forming a cone-shaped toroid. In this figure, C and D show the X-ray radiographs of the experimental plasma. The analogous petroglyph recordings, the well-known caterpillar and ladder, are shown to the far right. These figures are a collection of caterpillar and ladder category petroglyphs found worldwide. It is meaningful that caterpillars and ladders are found in association. Where the toroid stack consists of both spheroidal and flattened toroids, the optical radiation is brightest where the plasma is densest, i.e. closest to the edges of the toroids. This leads to a less well-known but still common petroglyph known as pipette. The pipettes shown in this figure all have symmetrical pairs of eyes. However, many petroglyphs simply show the outline of a pipette without any indication of hot spots or, quote, eyes. Experimental and petroglyph representations of these nonlinear column instability morphologies described in this figure are shown here. The petroglyph carvers have managed to capture all of the phases of the Z-pinch instability seen in the laboratory. These phases include the ladder and enclosed ellipsoidal topmost toroids. Some show the eyes of the bottom spheroidal toroids, yet to be affected by the currents of the neighboring toroids. Perhaps the most important feature depicted in the petroglyphs shown here is the curling of the edges of the flattened toroids. This feature is exact enough so that a time motion representation of the curling can be made and directly compared to its experimental counterpart. The curling or folding progression thus provides time information when the petroglyphs are scaled to laboratory data. The time scaling will be given in another paper. B. Vortices. With increasing current, the tips of the ladder rungs begin to curl and form a vortex. With yet a stronger current, the toroids themselves roll up, as shown here. This image provides the first direct evidence of the exactness to which petroglyphs were carved in spite of cultural influences and interpretation. The ladder rungs are stacked medium current toroids, are shown to fold and bend as do the laboratory photographs. Subtle changes in the petroglyphs corresponding to the plasma instability morphologies have been reproduced with precise accuracy, even including, in proper order, the admixture of toroid types. In all cases, the topmost toroid, the terminus in an electrical discharge, is indeed at the top of the petroglyphs and shows the transition of the pincher-type shape associated with the so-called scorpion petroglyphs into a folded petal as the top toroids fold up and close on themselves. Likewise, the slight upward bend of a flattened toroid at the middle of the column, its eventual curling at the end of the toroid, and the nearly square vortex folding into knots has been accurately portrayed. The accuracy of these MHD instabilities suggests that an appreciable amount of time of a particular morphology was visible to the petroglyph carvers. C. Intense current vortex deformation. Further along the current rise, the vortices morph into a variety of cupular or cone shapes. This figure shows experimental and petroglyph recordings of this phenomena. The downwardly shaped cup figures or mushrooms are a common theme in petroglyphs. The frames on the left are radiographs or radiograph-derived data, while those on the right are petroglyphs. 14. Universality of the basic plasma instability. If an intense aurora were the source for unusual bright objects seen in the nighttime sky, these objects would have been observed worldwide. What would be observed depends on a number of physical properties of the auroral funnel, and in the current-carrying magnetosphere tail. These include the intensity of the current-producing instability, the intensity and duration of sporadic current pulses within the auroral plasma column, and the orientation of a column undergoing non-azimuthally symmetric motions. While the previous figures have suggested that the phenomena was universally seen, what could be observed would depend on the observer's location on Earth and whether or not the entire column was visible or illuminated, or some portion of it, as in auroral displays today. Here's a collection of one of the most common petroglyphs encountered in the field, the squatter. It is usually interpreted as a human figure or anthropomorph with squatting-like legs and either upturned or downturned or mixed arms. It is unfortunate that this one morphology has been interpreted in modern times as representing a human or an anthropomorph. As such, it is widely ignored in favor of more exotic and realistic petroglyph forms. Perhaps for this reason, petroglyphs have been viewed as dumb history. In reality, the forms shown here mimic closely phenomena associated with the highest energy releases known, some of whose instability shapes were not known even a few years ago. This figure also shows that this basic shape was recorded independently of cultural bias or embellishment found on other petroglyphs. The anthropomorphs shown in this figure have several variations. The basic squatter depicted, the squatter with a bar or belly at the midsection, the squatter with either one or two dots on either side of the midsection, the squatter with two dots around the anthropomorphic head, often drawn as extended ears, and the extension of the basic shape to reptiles, etc. The extremities may be upturned, downturned, mixed, sometimes shown with 3-digit fingers or toes. There is perhaps no way of estimating how often this figure occurs, carved, pecked, or scratched on rock. It may have existed in inestimable numbers. The remainder of this section investigates the variations associated with the basic shape and why this is the basic instability shape. A. Azimuthal current ring structure formation. In addition to the auroral plasma column instabilities, an other well-known instability type occurs for intense currents having a slow rise time. Because of the azimuthal currents and strong interactive forces, the flattened toroids merge to reduce the number of apparent toroids. The enclosed ellipsoidal topmost structure is present, but the central toroids combine to form a single azimuthal current-carrying toroid. The geometry for this configuration is shown here. In this case, the instability consists of a top electrode consisting of a few toroids that have folded and closed to produce a central bulb, an upward or downward cup, a central plasma toroid, and a bottom, usually downward turned toroidal cup. Since it is an electrode, The cup torus at either end can take on a number of shapes. Usually the top electrode shows a variety of patterns. The patterns can be lightning-like, ellipsoidal, triangular that can resemble the shape of a bird, a lightning bolt, or multiple filament current terminations. This figure shows a number of petroglyphs found globally that share this peculiar geometry. Another variation on the azimuthal current ring structure formation is petroglyphs that have symmetrical dot-like enhanced earlobes or symmetrical dots at the lower extremity of the interpreted figure. The top image here is the instability cross-section. The bottom picture has been superposed with elements of the plasma instability. At the top of this figure, two toroids can be made out enclosing the central bulb. At midsection, a toroid such as that shown here, but slightly warped, is seen. Beneath this is a highly flattened and warped toroid followed by the usual conical or cup-bottom terminus as at the bottom of this figure. When viewed obliquely, the toroid is obvious, and petroglyphs depicting the left side of this figure are omnipresent. Note that the brightest plasma is at the edges except for the toroid, where denser and brighter plasma is innermost. At times, as the sporadic current pulse travels along the plasma column, 1, 2, or more toroids are seen in line of sight emission. This image shows yet another representation of this same class of petroglyph. A different perspective of this same instability is shown on the left side of this figure. In this case, the instability is shown at a somewhat later time when the central toroids have merged into the oblate shape at the center. The central feature can be accurately represented by a toroid, a flattened toroid either tubular or warped, an ellipsoid, or no apparent toroid at all. The visibility of the backside of the top cup is echoed in the petroglyphs that show the same shape around the central plasma bulb. Some show the central orb as either fully or partially enclosed. B. Aurora luminance. The luminance of a bright aurora today, when scaled to a catastrophic aurora, could be expected to produce instabilities whose luminance varied in proportion to the current within the pinched column. For this case, the luminance might increase, saturating the individual instability features as sporadic current pulses propagated along the column. For these luminances, the plasma instability configuration shown here would take on a new appearance, such as this figure. The plasma cups shown on the left represent the topmost terminus of a column shown here. It is of interest to note that some of the petroglyphs on the right of this figure show an equivalence of a plasma trifurcation at the bottom of the figures. C. Cocopelli. No description of petroglyphs would be complete without the mention of Cocopelli, the flute-playing figure that has inspired surprisingly far-ranging folk stories. With little cultural embellishments to the image, these are found worldwide. This image shows a collection of Cocopelli figures. At the top are two examples taken from a plasma discharge. These figures are respectively early and late-time photographs of the discharge. Whether or not the subjective interpretation of these shapes would result in the small sample of petroglyphs shown below is left to the reader. 15. Instabilities in the upper plasma sheet and their correlation to petroglyphs. The polar cap and magnetospheric cusp regions are roughly conical in shape as the inflowing solar wind flows down. Here shows the overall geometry. Like all plasma, the surface properties are both cellular and filamentary, as shown here, displaying an almost diamond pattern in the upper cone. The two figures below the plasma photographs are petroglyphs displaying essentially the same morphology as the plasma. Some petroglyphs have even captured closely the diamond and filamentary patterns. This will be presented in another paper. The similarity between petroglyphs and a converging plasma region is shown here. Three important features are observable. Two arm-like shapes at the top of the inflow, striations in the body of the column, and plasma feature at top center. A. Plasma cup. Both the cup, a deformed plasma toroid, and the return current are open to a number of interpretations if related to petroglyphs. These show a marked dependency on the cultural background of the petroglyph artist. It can be interpreted as a duck, bird, triangle, or even a head topped by a folded back elephant's trunk. At time, if the return current was sufficiently bright, a snakehead or lightning bolt could be interpreted. This figure shows some examples of both the plasma, topmost geometry, and some of the bird-like interpretations. This is a very common plasma profile. Dependent upon the oblateness and the tilt of the structure, it can be interpreted to represent a duck, a boat, the body of an animal, or an elongated or billed bird, or even a rabbit. B. Terminus. It is common for plasma clusters to have protrusions very much resembling feet, head, or tails of anthropomorphs or animals. The protrusions are part of the termini or filamentary currents running through and from the plasma. An example of termini from an intense discharge is shown here. In this case, two discharge strokes have trifurcated at the bottom conductor, such as a plasma sheet, to allow the current conduction path to continue. The topology closely resembles petroglyphs of animals, mountain sheep, or dogs and foxes in the American Southwest. Similar canine species in Australia, and oxen or oxen-like species in other parts of the world. Good examples can be found among the previous digital petroglyph images. 16. Shock phenomena petroglyphs. A large number of petroglyphs can be connected to the impulse shock instabilities rather than plasma instabilities. This figure shows supersonic shocked interface experimental data, while at the bottom of the figure are shown a collection of horn profiles from petroglyphs of presumed bighorn sheep in the western U.S. Another example of a shock-initiated hydrodynamic instability is shown here. On the left is an experimental photograph at late time, while on the right is a multiple-row mushroom-like petroglyph category depiction. We now turn to another class of petroglyph, those associated with the upward view on an intense aurora as depicted here. 17. Petroglyphs associated with the circular auroral plasma. Sections 2 through 16 were concerned with the Z-pinch instabilities that occur along the plasma column as seen in the lower center. We now turn to images that would be seen in an upward view of the intense aurora. These are studied using high energy density experiments and objects from Antiquity. A. Mega-ampere particle beams, 56 and 28-fold symmetry. A solid beam of charged particles tends to form hollow cylinders that may filament into individual currents. When observed from below, the pattern consists of circles, circular rings of bright spots, and intense electrical discharge streamers connecting the inner structure to the outer structure. This figure shows a 0.6 mm thick titanium witness plate that has been placed 15 centimeters in front of a 100 kg sub-megaampere charged particle beam. Initially, the particle beam was cylindrical, but after traveling the 15 centimeters has filamented. The wavelength of filamentation depends on the cylindrical thickness of a hollow beam. In the sub-gigaampere range, the maximum number of self-pinched filaments allowed before the cylindrical magnetic field will no longer split into islands for the parameters has been found to be 56. Modeling of 56 parallel electrical currents into 2 and 3 dimensions was carried out with a large-scale MHD code. These results verify that individual current filaments were maintained by their azimuthal self-magnetic fields, a property lost by increasing the number of electrical current filaments. The scaling is constant for a given hollow beam thickness, from microampere beams to multi-megaampere beams and beam diameters of millimeters to thousands of kilometers. That is, the same filamentation and vortices apply to auroral plasmas. Because the electrical current carrying filaments are parallel, they attract via the Biot-Savart force in pairs, but sometimes 3. This reduces the 56 filaments over time to 28 filaments, hence the 56 and 28-fold symmetry patterns. In actuality, during the pairing, any number of filaments less than 56 may be recorded as pairing is not synchronized to occur uniformly. However, there are temporarily stable or longer state durations at 42, 35, 28, 14, 7, and 4 filaments. Each pair formation is a vortex that becomes increasingly complex, as do the instabilities in today's auroras as they decrease in number by merger. B. Records from Antiquity with 56 and 28-fold symmetry. The number of 56 and 28-fold symmetry objects from Antiquity is manifest. These range from concentrical petroglyphs around the world to geoglyphs, or stone rings, megaliths, and other constructs. The most renowned of the 56-fold symmetric megaliths is Stonehenge. Stonehenge is a unique structure, a megalithic ruin located west of the town of Amesbury, Wiltshire, UK. It is concentric in shape, having 2 outer banks of earth, approximately 100 meters in diameter, circular with gaps. Adjacent to surrounding banks are circular and half-circular ditches, each with a radius of 5 to 6 meters, and each having a 3 concentric pattern. Within the banks are the arbor holes, now filled marker holes equally spaced at 56 points around a great circle that cut across the small concentric ditches. Geometrically inward, the next named feature are the Y-hole, 30 in number. These are nearly symmetrically located on a concentrical circle. The next concentrical circle is made up of Z-holes. Noteworthy of both the Y and Z holes, in contrast to the other parts of the megalith, is that they are not cylindrically symmetric. Both have a bulge at approximately the same azimuthal position, where there is a displacement outwards between neighboring holes. The Z-hole circle has a large displacement. There are 30 holes on this circle, 28 of which are readily visible. The next concentric is the sarsen circle, 33 meters in diameter, originally comprised of 30 upright sandstone blocks standing on average 4 meters above the ground. They originally supported sarsen lintels forming a continuous circle around the top. Inside the sarsen circle is the bluestone circle. The term bluestone refers to various types of mostly igneous rocks, including dolerites, rhyolites, and volcanic ash. It also includes some sandstones. In color, they are actually gray-red. The bluestones at Stonehenge are believed to have originated from various outcrops in the Preseli Hills in southwest Wales. How they were transported to the site at Stonehenge has been the subject of much speculation. The bluestones are on average 1¼ meters wide and 0.75 meters deep. These pillars stand 1.8 meters high and originally numbered 35. Periodically placed between the outer sarsen circle and the next concentric, a horseshoe of sarsen, the trilithons are 10 upright stones arranged as 5 freestanding pairs, each with a single horizontal lintel. They were erected with the sarsen circle in the form of a horseshoe with the open side facing northeast towards the main entrance of the monument. They were arranged symmetrically and graded in height. The tallest is in the central position. The trilithons are the most impressive feature of the monument, the heaviest of which weighs nearly 45 tons. Inside the trilithon horseshoe is another horseshoe of bluestone pillars. An altar stone in front of the center trilithons completes the main structure of Stonehenge. Additional stones mark the way to the avenue or cursus, a 2.8-kilometer long earthwork in the shape of a tail running linearly outwards from the horseshoes for 500 meters, then curving southeast. The dating of the construction of Stonehenge by English Heritage from 14 samples, primarily antlers, is 3020 to 2910 BC for the surrounding ditch, and Aubrey holes to 2270 to 1930 BC for the bluestone horseshoe. The Z holes are estimated at 2850 to 2480 BC, the same date as given the sarsen circle. The concentric nature of the main monument and the inadequacy of the recording of many of the relationships which exist leads to a shortage of direct stratigraphic relationships. C. Old concentric petroglyphs and pictographs with 56 and 28-fold symmetry. The old concentrics are among the most ancient of petroglyphs and pictographs. The carvings have long since reverted to the coloration of the rock patina onto which they were embedded. The paintings have leached into the rock, greatly dulling their appearance. As examples of 56-fold symmetric concentrics, we shall take 3 representative examples. The first is one of the opening plates of pictographs and petroglyphs of the Oregon country by Loring and Loring. In particular, Plate 3, a photograph of their Site 34, 4 o'clock rapids on the East Rim, Klickitat Country, Washington. This petroglyph is one that the Lorings described as outstanding and appeared to be very old. The Lorings from 1964 to 1968 took many photographs and rubbings of the deeply carved petroglyphs flooded by the J-Day Dam in April 1968. The second example is a pictograph downstream of 4 o'clock rapids at J-Day Bar, the Lorings Site 29. The third example is from northern Arizona, 1,450 kilometers southeast of the Columbia River Basin. In this figure are overlays of these 3 petroglyphs on a reconstruction image of Stonehenge. Each petroglyph shows slightly different detail. The top left petroglyph has apparently captured a later time image of the Aurora, as some of the outer dots are starting to undergo a diachotron instability rotational pairing, as was also recorded on the witness plate in this figure. Both the top overlays have recorded the inner filament electrical streamers between the inner dot circles, or electrical currents in forward synchrotron radiation light emission. The bottom left petroglyph has recorded the streamers between the two outer dots. The 4 o'clock Rapids petroglyph is about 60 centimeters in diameter, while Stonehenge is approximately 100 meters in diameter. However, an anomaly exists as illustrated here on the top left. Loring's reproduction shows a ring of outer dots that are not seen in the photograph. Moreover, the other photographs of this petroglyph before flooding show no indication of an outer ring of dots. Mid-20th century chalk enhancement photographs also do not provide evidence for the existence of an outer ring of dots. Through image analysis, we have recovered an outer ring of dots, precisely where the Lorings found them. 3 of the underside outer holes were protected and still deep. Thus, like Stonehenge, it would appear as if the outer holes were constructed much earlier than the inner holes, time enough for the outer holes to be very nearly worn away. Another possibility is that the central features were reworked over time. While many such images have been found, we shall cite the next 5. The 5th is found 1,479 kilometers to the southeast. 2 images nearly directly north are found 7,466 and 7,817 kilometers away, respectively. Another image is at 10,715 kilometers to the west and slightly south, with no inner structure. The last of the 5 cited is 8,926 kilometers to the northeast. Here on the top left depicts a 56-ray pictograph from the Wajana site at the Wanaliri Rock Art Caves in northwest Kimberley, Western Australia. The thicker rays at the upper left are part of a partially overdrawn larger pictograph. The image at the top right is the Arizona petroglyph. As drawn, the Wajana has shortened lower streamers. The concentric is elliptical. A rod is also drawn to the center of this pictograph. Image analysis allows the two to overlay precisely to the extent that it is difficult to discern differences in the rays between the two, but only if the Wajana is digitally tilted at an angle of 45.3 degrees. This is shown at the bottom of this figure. The gray-white embossed figure is the Arizona petroglyph, while the Australian pictograph is the flat black overlay. The gray-white embossed figure is the Arizona petroglyph, while the Australian pictograph is the flat black overlay. This comparison technique was forced by the nearly exact overlay of the rays of the two, making it difficult to distinguish one from the other. The apparent number of rays in the Arizona petroglyph is 47, but 56 when the thick ray at 4 o'clock is separated into 3 rays, and the thick rays at 9:30, 10:30, and 12:30 are each separated into 2. The need to tilt the Australian pictograph for an exact fit when projected into space suggests that the length and size of the intense aurora greatly exceeds that observed today. Painted over the upper left of the 56-ray Wajana are rays from a second larger Wajana image. This image too has a periodic 56-ray pattern. However, 30% of the rays were never drawn at the bottom of the image. That this is a younger image, in addition to it being painted on the top of the older image, is that the tips of the rays apparently have well-developed curls or vortices painted as blobs. The missing bottom rays also suggest that this is a horizon image. Other 56-fold images are found as far as 15,000 kilometers away, so that different angles of observation should allow the location of the incoming plasma to be determined. For example, this figure shows Site 34 rings overlaid on the 3 petroglyph pictograph examples in Stonehenge. The Site 34 rings were generated from the 4 o'clock Columbia River petroglyph, then overlaid on the other images. A slight skewness of this petroglyph is apparent towards the lower right corner as seen in the blind rings. This indicates a small obliqueness of observation as seen from the Columbia River. Newer concentrics and spirals easily discerned on rock generally are less precisely drawn but do not include embellishments found in electrical discharges at later time. The evolution of these morphologies will be discussed in another paper. 18. Discussion and conclusion. A discovery that the basic petroglyph morphologies are the same as those recorded in extremely high energy density discharges has opened up a means to unravel the origin of these apparently crude, misdrawn, and jumbled figures found in uncounted numbers around the Earth. Drawn in heteromax style, these ancient patterns could mimic and replicate high-energy phenomena that would be recorded on a non-erasable plasma display screen. Many petroglyphs, apparently recorded several millennia ago, have a plasma discharge or instability counterpart, some on a one-to-one or overlay basis. More striking is that the images recorded on rock are the only images found in extreme energy density experiments. No other morphology types or patterns are observed. The instability is that associated with an intense current carrying column of plasma which undergoes both sausage and helix deformations. Such a current would be produced if the solar flux from the sun were to increase 1 or 2 magnitudes, or if another source of plasma were to enter the solar system. This has followed the evolution of a Z-pinch from the initiation of instabilities in a column conducting mild currents to the helical and sausage instabilities as the current increases to extremely intense current instabilities. While the morphing of the instability is a continuous process to peak current, we have found it convenient to delineate the instability profile into 84 categories. Not all are shown in this paper. The sausage and helical MHD, or magnetic fluid, instabilities occur in the inner cylinder of plasma, pinched by its own azimuthal or surrounding magnetic fields produced by the intense current it carries. The evolution of this instability is well known in a linear regime that includes the pinching of the column into a stack of spheroid plasmas, usually 9 in number, that contain azimuthal current toroids, the original pinch magnetic fields. The electrons with the plasma toroids are relativistic, producing beams of synchrotron radiation observable in the visible. Hot plasmas emit radiation across the visible and radio spectrum. However, the emission often does not always have a thermal origin. Collisional processes also produce visible light within the column whose luminosity varies with the current intensity and sporadic current pulses. The luminosity and the observer's position in relation to the column determine how much of the instability is seen. In familiar terms, the linear instability consists of stacks of spheroids, stacks of toroids, stacks of double radiation, bright spots within the toroids, eye masks, pronounced nose features accompanying the eyes, and complex X-shaped separatrix patterns. The patterns are not shown in this paper. With increasing current, the instabilities enter the nonlinear and chaotic regime. The effect is a rapid inward motion of the pinch regions so as to form a stack of toroids. These are connected by a central bar running vertically through them. The extreme pressures cause the toroids to flatten and produce a single rod ladder configuration of disks. The next phase of evolution is the warping and flattening of the disks, which ultimately start to roll up at the edges, producing cup-like, then mushroom instability shapes. The uppermost or anode cups converge and fold to produce a bulb at the very top of the column surrounded by cups in various stages of folding. Generally, there is a mixture of toroid types throughout the column: tubular, flat, disc, cone, distorted, and cup shapes. Sometimes a single tubular or flat or distorted toroid is left at the center, while the bottommost or cathode consists of a cup that is turned down towards its terminus that may be sheet plasma. The single rod in all cases is present at the center of the stack from top to bottom. The anode end of the stack is the most interesting, producing various cup shapes and allowing lightning-like discharges to its terminus. Although discharges are also observed from the cathode end and sometimes between the toroids or outwards from the toroids for appreciable distances. These are the signatures of high-voltage discharges, as are trifurcated bolts found at the ends of any conductor. Plasma flowing in along converging magnetic fields produce a well-defined Y shape. Inflowing plasma, as in an intense aurora, is marked by a head of circular rings and radial rays, and 1 or 2 spiral discharge channels along the length of the aurora. Beneath the head, the plasma column shows a number of patterns consisting of a horizontal and helical filaments, diamond or separatrix patterns. For example, square vortex patterns as well as the previously shown instability shapes. When a shock wave produced by sporadic current pulses impacts the plasma morphologies mentioned above, these morphologies are altered in striking ways by hydrodynamic instabilities. Arms become wings, and cups become altered by the same instability patterns. These instabilities eventually grow into threefold patterns, such as what's shown here. Experimentally, plasmas scale at least 14 orders of magnitude and hypothesized to scale at least 27 orders of magnitude. That is, the instabilities and the growth rates associated with microampere currents are the same when scaled to those found in several multi-megaampere currents measured in situ in the solar system. In association with petroglyphs, this indicates that the relative timescales for the MHD instabilities carved in rock follow a known experimental sequence to the extent that time-motion sequence of petroglyph patterns can be generated and put alongside the time-motion recordings of plasma instabilities. Absolute times cannot, however, be ascertained in this way. When scaled to an intense aurora whose dimensions may exceed 50,000 kilometers for the outer cusp region, a relative time sequence can be unfolded. For example, the nuances captured in the bottom right of this image can be explained. The inward rise on axis along with the upward folding of the outer edges of the carved lines and transition to edge curling, a phenomena recorded in intense electrical discharge radiographs, could not have been known to prehistoric man unless he witnessed the same event in the sky. Scaling to the plasma dimensions suggests that each of the patterns shown here could have occurred repeatedly over months or a decade. The known plasma and shockwave instability types, when scaled from experimental to space plasma dimensions, suggests that an intense auroral event lasting at least a few centuries. The newer concentrics, especially those with inner patterns, not shown, and the unwinding spirals provide information about the final cessation of intense incoming plasma flux. On the other hand, the ancient concentrics and spirals, the remains of some having been cut and carved 8 centimeters deep in granite, suggest that intense auroral events were a common occurrence for at least a few centuries, if not millennia. The patterns are representative of a long-term period of typically quiescent aurora. The methodology used in analyzing petroglyphs and their comparison to extremely high energy density plasmas was based on creating a digital database of several tens of thousands of petroglyphs from around the world. Where possible, the following information was included in the database: information about the nature of the physical properties, type of rock used, facing direction, most probable field of view, longitude, latitude, altitude, and other petroglyphs in association. Again, where possible, the location and facing of the petroglyphs were plotted on 3D topographic maps in a search for a preferred field of view and thus the height and location of the aurora. This analysis is ongoing, but initial results suggest 3 epochs where in a flurry of activity petroglyphs were recorded worldwide. The number of millennia or centuries involved remains unknown. The discovery of buried horizontal petroglyphs in New Mexico and Australia, above which the carbon from campfires was found, suggests that the epochs occurred within a time period of 10,000 BC to 2000 BC. This corresponds well with recent plasma extraction dating methods by Rowe and Steelman for pictographs having the same patterns as the petroglyphs in this paper. 2 important classes of petroglyphs, spirals and concentric horseshoes, are not discussed in this paper. These map the Birkeland currents as depicted here and provide quantitative information on the electrical parameters. These, including solar wind magnetosphere interactions, are being studied with Tristan and will be presented elsewhere. I would like to recognize Anthony Peratt as a personal hero in helping define what I've been seeking. Anthony Peratt received the BSSEE degree from California State Polytechnic University, Pomona in 1964, and the MSEE degree and the PhD degree in electrical engineering from the University of Southern California, USC, Los Angeles 1967 and 1971, respectively. From 1972 to 1979, he was a staff member with the Lawrence Livermore National Laboratory, Livermore, California. From 1975 to 1977, he was a guest physicist with the Max Planck Institute for Plasma Physics, Garching, Germany. From 1981 to the present, he has been with the Los Alamos National Laboratory, Los Alamos, New Mexico. In 1985, he was a guest scientist with the Alphen Laboratory, Royal Institute of Technology, Stockholm, Sweden. From 1995 to 1999, he was with the Applied Theoretical Physics Division, Associate Laboratory Directorate for the Experimental Programs, and he was a scientific advisor to the U.S. Department of Energy. He authored Physics of the Plasma Universe, Berlin, Germany, Springer Verlag, 1992, and was an editor on Plasma Astrophysicist and Cosmology, Norwell, Massachusetts, Clura, 1995, and Advanced Topics in Space and Astrophysical Plasmas, Norwell, Massachusetts, Clura, 1997. He has served as session organizer for space plasmas at the IEEE International Conference on Plasma Science from 1987 to 1989. His research interests include numerical and experimental contributions to high-energy density plasmas and intense particle beams, inertial confinement fusion, explosively driven pulsed power generators, lasers, intense power microwave sources, particles, high-energy density phenomena, new concepts in space propulsion and high-performance computing, plasma cosmogony, and cosmology. Dr. Peratt was the guest editor for the IEEE Transactions on Plasma Science special issues on space plasmas in 1986, 1989, 1990, 1992, 2000, and 2003. He was the organizer of the IEEE International Workshops on Space Plasmas in 1989, 1991, 1993, 1995 through 1998, and 2003. He has been an associate editor with the IEEE Transactions on Plasma Science since 1989. He was an elected member of the IEEE Nuclear and Plasma Science Society, or NPSS, Executive Committee XCOM from 1987 to 1989 and from 1995 to 1997. He was the general chairman of the IEEE International Conference on Plasma Science, Santa Fe, New Mexico in 1994. He was the IEEE NPSS XCOM vice chairman and was elected to the IEEE NPSS Administrative Committee, both in 1997. He received the U.S. Department of Energy Distinguished Performance Award in both 1987 and 1999, the IEEE Distinguished Lecturer Award in 1993, and was a Norwegian Academy of Science and Letters, University of Oslo Physics Department, and Norsk Hydro Christian Birkeland Lecturer in 1995. He is a member of the American Physical Society, American Astronomical Society, and Eta Kappa Nu. I want to personally say thank you, Dr. Peratt. This is, in my opinion, the most important empirical evidence ever uncovered in modern history.